Okay, welcome everyone. I think we can start now. So thank you for joining us for today's webinar. My name is Corentin Jouvet and I'm JMAG Sales Manager at PowerSys. Just as a very short introduction, PowerSys is a leading provider of software solutions and services for electrification in several fields that you can see here. The one we will cover today is electromagnetics. Today, during this webinar, we are presenting how to address electric motor challenges in aerospace application using JMAG software. To develop this topic, we are really happy to welcome our guest speaker, Sergi Riba. Sergi is electric machine design engineer at Safran Electronics and Defense, and he's currently working with the Institute of Research and Technology, IRT, Saint-Exupéry, on the concept of the more electric aircraft. Sergi has a strong expertise in the electric motor technologies, thanks to his 15 years of experience in the aerospace industry. Our second speaker today is Yves Thiollier from PowerSys. Yves is a JMAG technical expert and he's in charge of providing support to JMAG European users. He also gives trainings and participates to the PowerSys consulting activities. Here is the agenda for today. During the first part of the webinar, Sergi will talk about the technological needs for aircraft's energy transition. In the second part of our presentation, Yves will present some solutions to address aerospace challenging using JMAG software. If you have any questions during the webinar, please type them into the chat box in your GoToWebinar control panel, and we will try to answer to the maximum of them by the end of the presentation. Now it's time for listening to Sergi. So I will let him go ahead. So now, Sergi, you are the presenter and you should be able to share your screen.
Hello, everyone. Thank you very much, Corentin, for this introduction. I hope that you can see my screen that I'm sharing to you.
Yes, you can see. Thank you, Sergi.
Okay. Well, thank you, everybody, to join today for this presentation. I'm going to speak about technological needs on electric machines for aerospace industry. Let's see okay. So this is a little bit the introduction. What we are going to see is, first of all, we'll see how all transportation-related industries, that are currently facing a deep transformation due to the reduction of resources on fossil resources. The emission in CO2 are contributing to a climate change. And we are going to see how the aerospace industry is participating to this emission and which is the expected evolution for next years. Then we will see the actions taken by aerospace industry to mitigate this impact. We'll see the objective, roadmap, the challenges, and the key technologies related to the transformation that is already going. On the third part, we'll focus on the electric machines to see which is the role that they play on this transformation, and we will see how the modeling and calculation tools are becoming essential to achieve very ambitious objectives on CO2 emission reduction. And at the end of the presentation, I will introduce the example of the IRT Saint-Exupéry, which I am collaborating since 2018. And you will see the project in which I'm working. So let's start by some key numbers about the impact of the aerospace industry. Today, 3% of global CO2 emissions are due to civil aviation. If we see the global on the whole planet contributors, we see that energy generation is the first contributor, and the transportation is around a quarter. Inside transportation, most of the part is related to route, to trucks and cars and buses and so on. And aerospace industry is at the same level as shipping, with 12 and 11%. But the thing is that air transportation is growing 7% average per year in RPK, and RPK is revenue passenger kilometer, so it's only the people that it's traveling, paying for traveling. We are not considering crew, and it's per kilometer, so that we can compare different transportations. So that means that every 15 years, passenger number are double, and we will see this chart is quite graphic. You see that what it means that passenger number it's doubling every 15 years. You see that the curve is really going high, and it's very resilient to different crises that we have been so far. We will see what happens with the coronavirus, but we cannot suppose that after that will continue as usual. What is going to happen with the fleet? The fleet is also going to double in 20 years. This is Airbus prevision, and what we see is that since we will need to replace some of current aircraft, the number of aircraft that will need to be built in 20 years, it's almost 40,000. That's out of airplanes to manufacture. So what the aerospace industry is going to do to reduce this impact? We have to know that there are already a reduction of 70% of CO2 emissions during the last 50 years. We see that depending on the new aircraft, we have some reduction, and there are still some technology solutions that may have still a 10% reduction on the view. But the International Civil Aviation Organization has had the commitment to get the carbon neutral ground for 2020 and to reduce the emissions, the CO2 emissions in 2050 about 50% in the reference on the year 2005. How to do that? Well, there are three ways to achieve this objective. The first one is, you can see on the chart, the aircraft technology in blue. Everything that is related to the aircraft and the design of the aircraft. Then we have operational improvements, because everything that is in ground also has an impact on the airports and so on. But then there is a big part on sustainable fuels, and also on CORSIA. CORSIA is a kind of program that wants to make compensation of carbon by the different solutions. So if we concentrate on the technological solutions, one axe is aircraft electrification. We have the evolutionary solution, which is the more electrical aircraft, which consists in the electrification of non-propulsive systems. We have some examples like the Airbus A380 and the Boeing 787. Those are the most recent aircrafts. And then we have the revolutionary way, which is the all-electrical aircraft, which has the non-propulsive, but also the propulsion, it's electric. And here is something that does not exist today, but we are working on. We will first focus to understand what a more electrical aircraft is. And we'll compare the power on the conventional airplane and a more electrical aircraft. First of all, we have the jet fuel that is responsible for the combustion and the propulsion of the aircraft. And from that, we extract around, we say, 5% of energy for different systems, which are some electric, some pneumatic, hydraulic, and mechanic. We know that, for instance, the pneumatic is used for all cabin in climate, for de-icing and many other solutions, and you see that there is a high power there because the efficiency is very low. For the more electric aircraft, we have that all the energy is extracted by generators driven by the propulsion, and then we act all the actuations by electrical energy. So we have the existing loads, the cabin pressurization, air condition, de-icing protection, flight control, landing gear, braking, everything, and engine ancillaries and fuel pumping, everything is electric. Those are the new electrical loads, and the global energy power will be around 1 megawatt, which is less than the addition of all the energy on the conventional one. This is because we have much better efficiency, much higher flexibility, because we can decide in any moment where to put the energy, and we have the priority loads, so we can disconnect some non-essential loads to drive the power where it is necessary. We have much better reliability because we have to know that hydraulic systems and pneumatic systems are not very reliable. They are very heavy, and it's very difficult sometimes to find the leaks and very costly to repair. So we will have many advantages with the more electrical aircraft. So let's see actually which is the current penetration of these electrical systems by aircraft type. And we see classical one, the Boeing 737. Everything is on the traditional pneumatic and hydraulic system for all these subsystems. On the Airbus, we see the A380 and the A350. We can see the flight control system is an electro-hydraulic actuator. It means that the actuator is hydraulic, but the pump is electrical. So there is not an hydraulic wiring everywhere, but it's just the pump electrical that activates the actuator. We can see the thrust reverser in these two aircraft are also electrical. And on the A350, we can see the wheels and brakes are also electrical. For the Boeing 787, which is the most interesting, is the pneumatic, the no-bleed system. It means that there's no air extraction on the turbine, and everything is, the air treatment is all electric. Also is the wheels and brakes. And at the end, we have the F-35, this is a military jet, in which the flight control system is fully electrical. That is the more interesting. What we see is that depending on every manufacturer and the technology that they handle and they control, everything is today mature for implementing in a flight aircraft, but it does not exist yet the plane that has all the subsystems in electrical way. That will come shortly, I think, for the next generation. So let's see what is going to be in the future. In this chart, you see the horizon for the more and for electrical aircraft. We see that in the upside, we have the axle. This is in French, but it's the battery density and energy of density of energy. And the ordinate is the power, electrical power and the voltage. You see that very soon we can have electric taxing, and all the subsystems that today are hydraulic, pneumatic, or whatever can be electrified. That is for the more electrical aircraft. Technology is already mature. It's a matter of implementing everything, which is quite complicated and to certify. But then very soon we will see very small drone, all electrical, hybrid helicopters, and later the VTOL or the small passenger aircraft. Then we have some barrier, technological barrier, that it's the 1000 volts embedded in the onboard in the airplane. Voltage with altitude is even more complicated to handle, and the high voltage for the airplane is a real problem today, and we need to work on that. So that's a little bit the horizon of what can we expect for the electrical and hybrid aircrafts. Which is the main obstacle, the challenges that we have. For the aircraft industry, everything is turning around the weight. So let's see, and particularly the batteries. So let's see the mass distribution of A320. We have the empty weight, it's 42 tons. Then we add 20 tons of jet fuel. We have a load capability with a full tank of another 11 tons. That makes the maximum that we can take on the takeoff, it's 33 tons. Knowing the jet fuel calorific value and the lithium-ion battery's energy density, we can have, if we would like to replace directly the kerosene by the batteries, that will make 800 tons of batteries. As you can imagine, this is completely impossible. So what is the technological objective today? We need much higher power density, starting by batteries. And the batteries today are at 180 watt-hour per kilogram. We'll need to go quite fast to 500. And then if we want to have a big aircraft for more than 100 passengers, it will be impossible. You cannot achieve 1000 watt-hour per kilogram. Electric machines are also need to make a contribution and to increase very importantly the density from 5 to 15 and then to 25 kilowatt per kilogram, and also for power electronics. Then we have to work a lot on the safety and reliability. For aircraft industry, it's a key here, and to be able to predict the reliability and robustness of electromechanical drive components, and also to assess and manage impacts of high voltage. As I said, this is a very important issue. But everything, it has to be with the manage of costs and the use of much standard as possible. So for the electric machines, what we see, the evolution of electric machines are tending to be higher power density, which is smaller machines for the same power, we will have higher thermal stress. But then if we increase voltage and DVDT due to the new power converters, are much faster, we will have higher direct constraints also. Increasing rotational speeds also for max density will increase iron loss and vibrations. So for this evolution, how do we respond? How do we address these objectives? We have many research areas, materials, mainly materials, high temperature, high conductivity, insulating, magnets, and then we have manufactured additive manufacturing and other manufacturing technologies. We have then to study other topologies, innovative, high-speed machines, superconducting, but also to have a look to the thermal management in order to address this high power that we have concentrated in small machines. In order to go further to all those research areas, we will need support for our calculation tools. That will be mainly modeling. We will need to have very accurate models and the computational calculation, which allows us to have the multi-physics modeling, which included thermal, iron loss, core loss, vibration, and everything. But also, in order to have the solution of innovative topologies, we need to work on topologic optimization of the electromagnetic circuit. That is a very important issue that it's quite complicated. It's not very mature, but we are working on this. So now, after showing which are the objectives and the reasons that leads to that, I will introduce the IRT Saint-Exupéry, which we are working in order to address all these problematics for the aeronautic industry, but not only. As you see, the IRT is a research institute that is located mainly in Toulouse with some other sites. And it's a multi-partner research with laboratories and industrial partners. And we have 4 different domains: high performance materials, more electric aircraft, system engineering and modeling, intelligent systems and communication. We work together with different knowledge on different domains. Industrial partners give the objectives, and laboratories and university give the knowledge, and together we are trying to find solutions in order to increase the maturity, the TRL, the technology readiness level, from 3 to 6. 3 would be an idea that is going out from a laboratory, and 6 is a demonstrator that it's already functional and operational, but has never been flying. So that will be ready for industrial to adapt it to the product. The key numbers on IRT: cumulative budget of more than 300 million from 2014 from 10 years. And we have more than 41 ongoing projects. We have laboratories, platforms, and equipment. We have more than 160 members. And human resources, we are around 320 people, and let's say half and half. Half are coming from industrial societies, and the other half is our IRT employees. We have experts, technical reference, PhD students, and postdocs. And the objective is to deliver technology transfer in terms of skills, reports, publication, training, intellectual property, software, patents, processes, everything, engineering support, demonstrations, and also, which is important, is the networking cross-industry synergy. We are working with this is mainly centered into the aerospace industry, but we are also working, as we said, with automotive, railway, and other industries that can be interested in the technologies that we are working on. And now, very fast, I will show you a little bit the project ePower Drive, in which I am working with a team. The idea is to give some answer to the questions before. So how to increase iron loss calculations. We are working on iron loss modeling. We are developing iron loss calculation model for a large domain of application. The objective is increased precision, and we will couple our model to a finite element software. And we are having creation of a characterization process to have a database for this model. The second step will be to increase availability and to assess the impact of HVDC and wide bandgap power converters on the electrical machine reliability. For that, we identified the failure modes, and we studied the state of the art on fail detection, health monitoring solutions, so that we can increase the availability of electrical machines. And then we explore the potential of additive magnetic refactoring applied to electrical machines. In the same way, we have been doing a state of the art, and we are doing an evaluation of the potential based on characterization of demonstrators. And the project members of this project are Safran, Libre Aerospace, Airbus, and Nidec, Leroy Sommer. And the laboratory for the PhD is the G3D lab on Grenoble. Now, I will show you a little bit the model in which we are working. It's a model based on hysteresis with two parts. It's a static part and a dynamic part, which depends on the induction, the history of this induction, and dVdt. So a static part depends on B and the history of B, and the dynamic part from B induction and dVdt. The static model is based on the plane model, and it's in addition of hysterons depending on the different states of the induction. So in different induction, here you have two examples with one hysteron and with two hysterons. You see that depending on the hysterons, we can build the cycle. Of course, we have much more hysterons, but then it would be too complicated to show the figure. The dynamic part is based on the loss surface model, and it's obtained by characterization. We have the dynamic field. It's the result of the field that we have measured in our laboratory, and we less the static model, the static part that we have just obtained from our static model. With this model, we can obtain the losses in our machine, which is the surface within the hysteresis cycle. So some results is some information in order to characterize and identify the process and characterize the material. We have a hysteresis graph with two Epstein frames. We have a single sheet tester and a rotational power tester, so that we can make measures in 1 and 2D for pulsational and rotational fields. And what we obtain is that we see that depending on the induction level, the saturation level, the number of and the harmonics and the quantity of these harmonics, we have different results. The lower is the second on the second line, first row. This is a very low induction cycle, so field losses, which has a 19% error. But for the rest, when the amplitudes are higher, we see that we have a very close result going from 0 to 6-7%, which is a very fair result compared to some other model that calculate iron loss. So the conclusion is the IRT allows to share industrial society's experience and the laboratory's knowledge, and we have the support of important technological test platforms with all this hysteresis graph, and partial results are very promising, and they meet members' expectations. So that is what we do in IRT, for example, just to address the problematic that I showed before. So that's all for my introduction. Thank you very much for your attention. And if you have any questions, I will be pleased to answer at the end of the presentation now at the turn to quarantine for introduction. Thank you very much.
Thank you, Sergi. Thank you for your presentation. So now we listen to Yves, who will show you some solution using JMAG.
Okay, thank you, Corentin. Can you hear me? It's okay?
Yes, we can hear you very well. Thank you.
Thank you. Thank you. Hello, everybody. So I am Yves, in charge of technical support for JMAG, and I will try to present you now some feature of JMAG to address the challenges exposed just previously by Sergi. So thank you, Sergi, for your presentation. Here is the program of this workshop. So initially it was a workshop, so we changed that into a webinar. So maybe many information. I will try to summarize everything in this webinar. I hope it will be not too much information and not too quick. So first, iron loss calculation method in JMAG examples. So we will review the current classical method. I would like then to talk about the new calculation method, and then understand the difference and comparing those methods. Then, of course, we will go to the thermal issue, but I would like also to talk about multiphysics and thermal stress, induction heating, and of course mapping. Then the last topic will be some fault management, like short circuit, for example, using JMAG-RT. So of course I will show you what is JMAG-RT. So creating behavior tables, that's the aim of JMAG-RT, and how to use those JMAG-RT and run the default investigation. And to finish, I can show you some latest improvement of the JMAG-RT tool in JMAG. So let's focus first on the iron loss calculation method in JMAG. The contents of this part will be to review the loss component, check the first classical method like FFT and the one we call in JMAG preset one, which is a mix of apply loop and FFT. Then we will check some measurement comparing those two methods. We will see some issues coming from those methods, some assumption and some issues, yes. And to overcome those issues, JMAG has what we call preset 2, which is the hysteresis modeling or hysteron play model. So that's the latest method shown by Sergi just previously. And the homogeneous method for the eddy current. And still we will compare all those calculation methods, and then I will open maybe 2 or 1 depending on the time case study. So let's start with the loss component. So here is what you know maybe, just a reminder. So we've got several types of losses: iron loss, copper loss, stray loss, mechanical loss. Mechanical loss, that's okay, that's the bearing, something like that. Stray loss, that's maybe the massive part, tanks, something like that. Copper loss, that's in the winding. And iron loss, that's mainly in the laminated part. So today we are going to review the method for calculating those iron losses here. So here is all the method you've got in JMAG. We've got the FFT method, which is identical for hysteresis loss calculation and eddy current loss calculation. Then we've got the preset one, which is apply loop for hysteresis loss, and FFT for eddy current. And the preset 2, the new one, which is hysteron play model for the hysteresis losses. And then we've got a mix of homogeneous method and measurement for eddy current. So I will detail you all those methods just later on. So here, as I told you, we are going to check iron loss calculation, okay, and then hysteresis loss and eddy current. First method would be the FFT method and preset one. So I will, all along the slides, you will see this small table here to let you know exactly which method we are reviewing and to avoid any confusion. So you will see what method we are talking about. So here you can see that we are going to first have a look to the FFT method. Those methods, so FFT and preset one, they are very classical. It's kind of Bertotti-based method post-calculation. So of course, those two methods, and especially FFT, are based conventionally on some measured data. Those data are usually provided by the material manufacturer. So here is an example. So those data, this is iron loss density versus flux density and versus frequency. So if you go to JMAG, you will get that kind of loss data here. In your toolbox on the right side, you've got the material database. You've got your soft magnetic material. If you open one of those, then you will see here in the loss tab, you will see that kind of table. So very, very classical. Let's go back to the presentation. So then how the FFT is working based on this data. This is what JMAG is doing. So you need to run first the FEA calculation, transient calculation or frequency response, doesn't matter. Usually it's transient calculation for motor. And in each element, JMAG will pick up, so let's focus on this small element. We will get the flux density waveform. JMAG will make an FFT. So it means that JMAG will get the frequency, the amount of flux density for this frequency. And so based on those iron loss density, JMAG could get the total iron loss for this small element. So this is how we get the total loss. Then the next issue is to now split that total amount of losses into hysteresis losses and eddy current losses. Let's have a look on what is exactly hysteresis losses. So this hysteresis losses corresponds to the amount of area of this loop. And classical expression could also be shown here. And you see that this hysteresis loss density is depending on the frequency. And then knowing that, if you run your calculation with a sinusoidal excitation or with a trapezoidal excitation, you could see that whatever is the waveform, there is no difference in the loop. You've got exactly the same area, so the losses should be same. And then we can get, so knowing those two assumptions before, we can get the eddy current losses by subtracting the hysteresis losses from the total losses. And because one is only depending on the frequency, so the hysteresis losses, we can plot that equation. So this is classical equation of losses divided by the frequency here. And also assuming that now this equation is linear, that's an assumption. That's not actual, because the actual one is not completely linear, but that's an assumption. Knowing that, now we can get the amount of kH of hysteresis losses by plotting these curves and getting the intersection with this axis here. Here is an example for this material. So plotting 2 points at lower frequency, we can get the kH, and by getting the interception of this p dot divided by f axis. So this is how now we can get, using the FFT, the amount of total losses. Go back here. So we can get it here, total losses, and then we can split and get hysteresis losses and eddy current with this equation, and especially this one to split the losses. However, there is another method which is implemented in preset 1 for hysteresis losses. Those method is called loop detection or apply loop. So it means that now minor loop and major loop are estimating by counting the peaks of flux density waveform. So if you've got the waveform, we can get some spikes here, and then we can assume some minor loop and some major loop, and you can see that those loops could be detected, and then the area of those loops can directly be calculated and get the amount of hysteresis losses by this method. So now if you compare FFT and preset 1, just a brief summary. So we've got the B flux density measured data, we've got total loss. We split that into hysteresis loss and eddy current losses. That's the FFT method. Still, for the preset one, we have no other solution than FFT for eddy current losses. So you can see that this part here, it's exactly the same. So we've got the B flux density measured data, total iron loss, and we split that into eddy current losses and hysteresis losses. And we will use that amount of eddy current losses, PE2, as the final and total, as the final eddy current losses. However, we've got this new method, the apply loop. So it means now hysteresis losses here will be the one to be subtracted to the total losses to get the real and total final iron losses. So it means no, it's not be subtracting, now it's be an addition. So it means that to get the total losses from this preset one, it will be the summation of this one and this one. And this iron losses here get from the FFT is no longer used. That's the assumption of the preset one. So still eddy current are calculated same way using FFT, but then hysteresis losses is calculated as apply loop, and then the total is the summation of the both PE2 and PH2. So let's compare FFT and preset one. Here is a ring core, and we will apply some sinusoidal waveform and square waveform, different frequencies, and here you can see results of FFT and preset one. So the first thing you could check is that, so in blue you've got the eddy current losses. You could see that whatever is the waveform and whatever is the method, we've got still the same amount, because you see that FFT is the one to be used, so it's exactly the same amount. But then now if you check hysteresis losses, you can see that the amount is not the same. So of course, if you use sinusoidal waveform, they are same. If you compare FFT and preset one, they are same, identical, because as I shown previously, there is no harmonic. Oh, no, I did not show this slide. It's the one after. There is no harmonic in the FFT because it's sinusoidal waveform, purely sinusoidal. But when you go to the square waveform, you see that, so in gray, hysteresis losses, if you compare FFT and preset one, you see that those amount of losses are not equivalent. And that's because in the FFT, the square waveform, some harmonic are introduced, and that could create and causing some error in the FFT method, because area should be same, so hysteresis losses should be same. And the FFT, now when you have square waveform, are causing some error. And of course, purely sinusoidal has no harmonic. So here you can see that this is the same amount. So we've got some verification with measurements. Here is a SPM motor non-load calculation at the moment. Okay, you can see in green measurement losses, then red joule loss, blue hysteresis losses. So you can see that using preset one, we are very close to measurement. That's not so bad, but still some issue. Still some losses are missing. Of course, verifying accuracy of iron loss at non-load is very good, but we also need to go to over operating point, because we need to check magnetic saturation and higher harmonic due to the drive. So we will switch to another working point. And here is, for example, a IPM motor. And you see that we are going now to introduce some also PWM waveform. And of course, you can see that at high frequency, the only sinusoidal excitation is missing some harmonic due to the PWM. So you can see that we are a bit far from the measurement with the sinusoidal waveform, and PWM waveform it's much closer to the measurement. So one key point to run that calculation is of course loss calculation, but also current waveform, because you can see that when you are using PWM, the current waveform has some high harmonic. So one issue is also to get accurate current waveform from the FEA calculation. And to do that, so JMAG RT has been used. So it means this is a behavior table. So it means we could have very small time step here. However, the calculation will be very quick because we are just using a behavior table created by JMAG. So it means that the calculation, even if the time is very small, the calculation will be not so big, and then we could get this current waveform, and then this current point sequence data is implemented into the FEA calculation. So we get a very accurate current waveform. Here you can see that the results with some more detail. Light blue, it's the measurement, and then eddy current losses. You can see that compared to the sinus excitation, you can see that eddy current losses are under-evaluated using sinus waveform. Okay, so we can see that now we are not so far from measurements, but maybe depending on cases, there are still some issue, and we are not completely fitting the measurement. So we are now going to switch to preset 2, and let's reviewing the issue of preset 1. So we may have some hysteresis loss issue due to the minor loop. In the method I showed you previously, so if we go back here, we are assuming that the loops are all identical, or let's say based on the first magnetization curves. Let's say initial pH curves you have specified in BH, in JMAG. So it means that the minor loop are not very well calculated in JMAG. So we may have some issue to evaluate hysteresis losses for minor loops. And then regarding the eddy current calculation, we have seen also that it is based on that kind of loss density data. Okay, so it means that if your harmonic are out of this range or in between those frequencies specified in your material database, the software, so JMAG, is interpolating when your frequency is in between those curves, or extrapolating when the harmonic are outside of this range. And this, okay, let's say interpolation is not so bad, but it's an issue. It's maybe a cause of inaccuracy, but the extrapolation is maybe the biggest issue here. So that's why this preset 2 is introduced. So preset 2 is a combination. So you can see that now we switch to this preset 2 here. It's a combination of hysteresis model. So several names could be found on the literature. So it's hysteron play model, hysteresis play model, hysteron play model, play hysteron. So that's for hysteresis losses. Then the next one is homogeneous method. This is for eddy current, and the several names are also given. In JMAG, it's also given, like, if I remember, eddy current in steel plate, something like that. But it's what you could find, it's a homogeneous method for calculating eddy current. So let's have a look to the play model first for hysteresis losses in preset 2. So it's closed BH curves, I told you, that are used for the FEA calculation. So in fact, all the loops are using this BH curves to get the amount of losses. So that's not so accurate. So the idea of the hysteron play model is to be able to reproduce any arbitrary BH loop, whatever is the working point, wherever it is located on the BH graph. And to do that, this model needs some new data, and we call that symmetric BH loop. So if you go to JMAG, so that kind of data is implemented in JMAG. JMAG has a database for that. So here you see that we've got the DC magnetic type. So this is the one I showed you previously. And we also have the hysteresis type. So that's some standard that have been measured and embedded into JMAG. So now if I open, for example, this one, and if I go to losses, and maybe if I zoom a bit, you could see that we've got not anymore loss density data, but we've got some flux density versus magnetic field, so real BH curves. One assumption is made here that it's just the going up direction. Of course, the going down will be symmetric, central symmetry to the origin. So this is the assumption. We just need to specify the going up direction. And of course, you need to measure that. If you don't want to use the one from JMAG, or if your material is not specified here, you need to make that measurement, and you need to respect some rules for the hysteron play model to work correctly. However, JMAG has also a tool which is create hysteresis curves. So this tool, you will be able to put your measurement directly, import measurement data, and JMAG will clean up this measurement data. You can filter some harmonic, you can remove some AC or some DC component if you have. You can add some interpolated loops, and etc. So this tool then will output some database directly that could directly be implemented here in JMAG and directly usable by JMAG after. So once you've got this symmetric loop, the hysteron play model, which is in fact a combination of hysteron, so you can see here different hysteron. We have a workshop on that. If you are interested in, maybe we could have some more meeting if you want, and I could show you how it is working exactly. So it's a combination, let's say a summation of different hysteron play model, and we apply some shape function to this hysteron play model, and summation of all those one, we are able to calculate actual minor loop. Here is an example. Here, what you could find in JMAG using this symmetric loop. So it means you don't need to measure all minor loop. You just measure that symmetric loop here, like this, and you can recreate all the minor loop. Of course, there are some assumption, or not assumption. There are some rules, and you also need to check the resolution of your simulate loop to be able to capture very small BH loop. So let's compare now preset 1 and preset 2. So if you remember, preset 1 is apply loop and preset 2 is hysteron play model. And here you can see that the loop are applied with some DC offset to change the working point on the BH curves. The orange one is 0 offset, so you can see here the area of the loop with the apply loop, and you see that whatever is the DC offset, you see that apply loop is the same area. However, if you use the play model, you can see that the play model can reflect the difference in the real area depending on the DC offset. Okay, so I hope now the preset 2 hysteron play model is clear. Let's switch now to the preset 2 homogeneous method. So homogeneous method, that's for the eddy current. So it means now we could calculate a different way the eddy current. And this is by adding some 1D additional calculation, FEA calculation inside the lamination. So here you can imagine that this is one lamination of your material here, and JMAG, so these small black lines means some 1D additional calculation inside the lamination. It means that JMAG will evaluate eddy current inside each lamination and will really calculate the eddy current depending on the fluctuation of the B and the electrical conductivity of your steel sheet here. So same as previously, so we are still having the B density in one element. So if we compare from the previous one, if we go back here, we are still having magnetic flux density because we ran the FEA calculation. In one element, we get the flux density and we made FFT and etc. So now let's go back here. We still have the magnetic flux density in one element and we run the hysteron play model and we get the amount of hysteresis losses by calculating this area. Same with eddy current and the homogeneous method. So we are focusing on maybe one element. We get this magnetic flux density. And now we will use this magnetic flux density as a boundary condition here. And here we assume that this is Z is the thickness of your lamination. And here 0, Z equals 0 means it's the middle of your lamination. So JMAG is assuming that on the other side of your lamination, the distribution will be the same. So the calculation is in fact run on half of a lamination. So here we are in the middle of the lamination and JMAG is assuming potential vector equals 0. And here potential vector is fixed using the magnetic flux density, which is here given by the finite element calculation. And then JMAG will be able to recalculate flux density distribution inside half of your lamination. So you can see that as spreading the magnetic flux density all along the thickness, or respreading the magnetic flux density along the thickness, and then calculate the corresponding eddy current. So as we compare apply loop and play model, now we can compare FFT and homogeneous method. So orange, you can see homogeneous method, and FFT, it's the blue one. And here is the frequency increase. And you can see that the extrapolation of eddy current, which are used in the FFT for high harmonic, increase the error significantly for very high harmonic. However, with this method, the homogeneous method, we still missing something because we are calculating very classical eddy current. It means it's eddy current calculated by the flux density fluctuation and the electrical conductivity. However, in total eddy current losses, we also have what we call the excess losses, and that are that could be classically due to the moving the walls of the small magnetic domain. So if you have only classical eddy current, so changing magnetic flux density or field, and you've got eddy current. But if you are considering the magnetic wall, then you need, if you change the H, then you will change this wall. And this is some additional losses, excess losses. And because we are just using electrical conductivity, then we are missing those excess losses. However, if we are back in the FFT, here, FFT method, because FFT method use measurement data provided by the manufacturer, so the classical loss density, the manufacturer has measured the losses, so it means eddy current includes all those losses. So it means the manufacturer are giving the total eddy current losses, including the excess losses. So using the FFT, it's already included that, but not in the homogeneous method, because it's really based on the electrical conductivity. So what we could do to overcome this issue is to get back to the measurement data again and to guess one correction coefficient. So here, for example, if you use the FFT or preset one, you can imagine that separation. So here the little gray is the classical, is the excess losses, and here this drawing here, it's the classical eddy current. And if you check the preset 2, you see that something is missing here. That's the classical excess losses. And here the idea is to guess a coefficient based on the measurement data to then correct the losses to get the total eddy current losses, to take into account the classical the excess losses as well. So yeah, this what I told you. So by using some measurement at low frequency, we can now include excess losses. And here is the new, let's say, new procedure for the calculation of the preset 2. So we've got some measured iron loss here. We get the symmetric loop, then we calculate with the preset 2 hysteresis loss and classical eddy current. But from those measurement losses, we can compare what we get with the classical and the measurement on some point. And with those points, we can guess this K coefficient. And then you can implement that in JMAG, this K coefficient for different magnetic flux density and for different frequency. So here is the curves that you can get. So this is some additional tool in JMAG to correct the homogeneous method to now fit the measurement. So still again, we are back to the measurement, but that's on the small part of the losses. Not all the eddy current are using measurements as it is done in preset 1. Just this small part is back to measurement and evaluated and corrected with some measurement data. So this is what is done in JMAG now for preset 2. So let's have a summary. So here you can see top of the table, it's hysteresis loss, eddy current loss is there. Here we've got the FFT, preset 1, preset 2. So the method, so here it's obtained hysteresis loss are obtained by loss separation. It's based, of course, on some measurement, cause of error, DC, offset, and non-sinusoidal flux density. Eddy current, it's the subtraction of the hysteresis losses to the total losses. Of course, it's based measurement, cause of error, extrapolation. So preset 1 for eddy currents, it's exactly the same. We saw that, so cause of error is extrapolation. But for preset 1, now we are using apply loop. So of course, it is still based on measurement, and here still the issue. So we have no this non-sinusoidal flux density issue, but we still have the DC offset issue. So this is why we are going to preset 2. So now this is what we call the hysteron play model. It's based on symmetrical loop. Here we've got the homogeneous method and for eddy current, and it's now based on resistivity. Maybe here cause of error, we could also put that it's for the excess losses, it's still based on some measurement, but it's now getting very good accuracy, because not all the eddy current losses are calculated on measurement. Maybe on cause of error of preset 2 using hysteron play model, cause of error could be the resolution of the symmetric loop or the way you measure the symmetric loop. So we have 2 case studies now. This is a SR motor. Okay, here is the model, here is the circuit. Okay, and here you can see the comparison between measurement preset 1 and preset 2. And of course, here you can see that hysteresis losses are the main cause of difference between preset 1 and preset 2. This is because in SR motor, we've got some big minor loop and with at a high saturation level. So this is why now we've got some big differences in hysteresis losses. We've got another study. Okay, maybe I will try to show you the setting in JMAG at the end of this example. This is an IPM motor, and this is the current waveform. So we are using PWM, and here you can see the difference between preset 1 and preset 2. And here you see that at high rotation speed with high frequency, you see that now hysteresis losses, okay, you've got a difference, but it's not so big. But now the issue is the eddy current, so the high harmonic, due to the extrapolation of the measurement, you can see we've got very big difference in eddy current. So depending on your motor, depending on your cases, maybe for SR motor, the critical issue is the hysteresis losses that are not so well evaluated by preset 1. Maybe on IPM with IPM motor with PWM current signal input, the eddy current are the issue, and maybe the FFT and it's the measurement, the extrapolation of the measurement cause the main error, the main issue. Okay, so maybe I could open maybe the IPM example. So I could show you the different settings in JMAG. Okay, so here is the model I show you. So that's a quarter model. Okay, so I can open this, and you see that I have some finite element calculation first with many time steps. So here you can see the current waveform. So here you can really see that we've got the PWM effect, okay? And then we've got different iron loss post calculation. So it is post calculation based on this FEM calculation. And here, for example, we've got the preset 2. So if you go to preset 2 and if you go to condition, iron loss, you can see that the settings are here. So it's using preset 2 here instead of preset 1. So preset 1, if you go to preset 1, that's apply loop and FFT, and preset 2, you see that it is now hysteresis model and eddy current in steel plate. This is what it is also called homogeneous method. And you need to specify the lamination thickness because, as I showed you previously, the JMAG will calculate inside each lamination. And of course, you can specify the number of calculation of 1D additional calculation you want in this half of a lamination. And then you can access to the losses as a classical way in JMAG, so contour plot, graph, and etc. So I just would like to show you the settings where it is done exactly. If I go back to the presentation, maybe next topic will be to compare the method, and I'll be back on some examples later on. So here's, maybe I can put in full screen. So here is the comparison of the different methods. So to compare all those three methods, 50, preset 1, and preset 2, we'll use this ring here. And we will apply some current, sometimes with no DC offset, sometimes with DC offset, and on different frequencies. So here you can see top, you've got no DC offset, bottom, you've got this 0.2 ampere DC offset here. Then you've got different frequencies, and in orange you've got hysteresis and eddy current. And okay, I have some question for you. So maybe that's not really question because you cannot answer now, but that's maybe some key point or topic to focus, and that could be interesting to focus on those points. So question one is why the range of losses decrease with offset. So you can see that here, if you are whatever the frequency and whatever the losses, type losses, here we've got so no DC offset, and here we've got DC offset. Okay, and you can see that the range is really decreased here with the DC offset. So it's in fact, if you check the flux density variation delta B, when you've got no DC offset, here you can see that the delta B is much bigger than you've got when you are at high flux density, so with some DC offset. So whatever is losses, maybe you will, whatever is the method you would get, and whatever the losses you are also focusing, you would get low losses. So this is why we've got first this range, which is smallest here with DC offset. Then question two, why hysteresis losses are larger at high frequency. So this is here, this case. So with the DC, with no DC offset, you can see that hysteresis losses here compared to preset 1 are higher hysteresis losses. So of course, we are using preset 2 and we are checking hysteresis losses, and as we have seen that it should not be have no harmonic, different frequency, okay, higher frequency, so it means more harmonic. However, we have seen that this is not just depending on the area, okay. So with no DC offset, we should not have not so big difference in preset 2 compared to preset 1. But in fact, we are checking hysteresis losses, but preset 2 not only affect hysteresis losses, we also have that homogeneous method. And in fact, now preset 2 has the skin effect, which is implemented. So it means that the flux near the surface become bigger. So here you see preset 2. You can imagine that this is a distance from your face, okay, still half of a lamination. And due to this skin effect, so due to this homogeneous method, the flux density inside each element that are close to the surface will be different. And here you can imagine point A, point B, and point C. Here you can see the flux density, which is now at point A, for example, the orange one is much more bigger. So this skin depth, due to the hysteron play model, will affect the flux density in the element, and then it will be reflected also on the hysteron play model, so on the hysteresis losses. Okay, let's go for question 3. Why eddy current larger at higher frequency with DC offset? So question 3 here, with DC offset. So now we are focusing on eddy current. So why they are also bigger with this DC offset now. So previously we check the hysteresis losses. Now we are checking the eddy current, and at with DC offset, high frequency. Okay, that's the question 2. So let's go to question 3, and here also it has DC offset. With the DC offset, also influence the skin depth as higher frequency. So it means that we will increase the skin depth and increase the eddy current losses due to this DC offset. So still here, this skin depth, which is now taken into account by eddy current, will also affect, of course, eddy current losses, and especially at high frequency. Let's go to question 4. So why hysteresis losses are smaller at lower frequency with DC offset? So here you see that with DC offset, we've got nearly, question 4, nearly no, or very, let's say very small, or let's say no hysteresis losses at the DC offset. Preset 2, so nearly no hysteresis. So then here we need to check the resolution of the hysteron play model, and maybe I can also show you JMAG again and display the losses. So the symmetric loop, and maybe here if we zoom, we can see that there are a delta B, okay, and this is what we call the resolution. And here you can see that in the material database provided by JMAG, so the resolution is 0.05 Tesla. That's the resolution of the hysteresis loop. And then so the limit of the hysteron play model say that the minimum loop, or the smallest loop that could be detected, is this delta B divided by 2. So it means that the amplitude of 0.1 Tesla, when we've got some DC offset, the amplitude, as we can see here, you can see the amplitude now, because of the DC offset, is very small and cannot be detected by this resolution. So the area of the loop becomes 0 because of the resolution of this hysteron play model. Then question 5, why eddy current smaller when there is no DC offset? So question 5 here. So you can see that we've got, compared to preset 1, we've got a lower eddy current, and especially here at higher high frequency, so with no DC offset. So in this calculation, we did not include this excess loss calculation, so the one based on measurement. So the explanation here is that in this calculation we did not specify the correction coefficient. So this is why we do not get those excess losses. So here those questions, maybe in your calculation you could have different issue, different question, but it might have some explanation. So you really need to focus on the method and how it is calculated in JMAG, and to very well understand. So depending on the phenomena you would like to capture, maybe method preset 1 or preset 2 are the best way to run the calculation. And you really need to have that kind of questioning like that to be sure that the method you are using is the good one. Then of course comes the calculation time. Of course, preset 2 is longer than preset 1. Preset 1 is a post calculation, very quick. However, preset 2 is now existing more than 5 or 6 years in JMAG, and at the very beginning that was quite long, I have to confess that. But now the developers have improved those methods, and the good point of this 1D calculation here is that you don't need a 3D mesh to do that. JMAG will smartly run some calculation here in the lamination thickness without having a very huge mesh and very high density mesh to draw each lamination. JMAG do that in smart way, and so no unuseful calculation are made. Everything is done by JMAG, and now the calculation time is really not so bad. So before switching to thermal calculation, we talk about the iron loss calculation, and the example I show you in JMAG, that was post calculation. So it means you have run this FFT, this transient calculation, and then you could run several different iron loss based on different method. However, those method, the preset 2, the preset 2 could not only be implemented as post calculation, but also as could be implemented during the transient calculation. So it means that now the transient calculation, the working point you are running, could take those losses into account. It means you could run, you could have the real hysteresis cycle for your working point in your transient calculation. You could have the eddy current losses included directly during your transient calculation. So here is an example of a ring, so 2D calculation. In green, you've got the ring, and in so here you've got the current. Okay, so it's a ring, circular ring. It's just a partial model, and I have run some calculation using hysteresis model during the transient calculation, and I have placed some probe. So here you can see some magnetic probe in the middle, so B and H, and the same with the hysteresis model, same position for the probe. And if you get now, if you make a B versus H on the two different model, you can really see that the one with the no hysteresis here is just staying on this BH curves here. However, the second one using the hysteron play model, so you can see that the B and the H during the transient calculation are following this BH curves. So it means that those two new methods, preset 2, is not only post calculation but could be also included in your transient calculation. Okay, so that's the end of the hysteresis loss. So let's switch now to thermal. So let's have a look. Oh, sorry, I missed one slide. So let's go now to the thermal calculation and JMAG coupling. So the contents of this part will be multiphysics in JMAG, so not only thermal. Then of course thermal. Maybe I will also show you thermal analysis in JMAG Express Online. This is totally free, anyone could use it. And maybe in aerospace, some people not only focus on motors, but maybe on heating of I don't know, some shaft or something like that. So induction hardening or checking some stresses due to thermal, something like that. And we will also see some link with third-party software in case you would like to run some more big thermal calculation. So let's look about thermal analysis and multiphysics in general in JMAG. So you could see that in JMAG you can perform magnetic, thermal, structural, and of course iron loss calculation. We talked about that previously. And in JMAG you can exchange some quantities. And for example, between magnetic and structural, so you can send the EM forces from the magnetic into the structural for stress, vibration, sound pressure. Of course, you can send the stress calculated into structural into the magnetic to evaluate iron loss. So maybe I can also show you that in JMAG. So I show you DC magnetic DC type, hysteresis type, so the one including the symmetric loop. But in JMAG, you also have something which is very useful. It's a stress-dependent material. So it means now you don't have only one pH curve, but you've got several depending on the load, and same for the losses. So that's for the preset one, so the classical loss density. You can see that this is versus stress. Okay, and you can also link magnetic to thermal. So loss is given by magnetic to thermal, and then temperature is sent back to magnetic. We will see that we could have some two-way coupling between magnetic and thermal. Of course, the magnetic calculation could send magnetic flux density to calculate iron loss, and now the losses are not coming from the magnetic itself, but from the iron loss, and still temperature is sent to magnetic. So those three analysis could be coupled. So let's have a look now to the magnetothermal coupling in JMAG. So thermal in JMAG, that's really only conduction and radiation only, no convection. It's not a CFD software, not fluid dynamics computation, but you can handle this convection phenomena by using heat transfer coefficient. It could be some fixed heat transfer coefficient on each faces of your motor, but you can also map some heat transfer coefficient density coming from a CFD software. And all the magnetic and thermal properties could have the thermal dependency. Of course, in JMAG, you could couple the magnetic and thermal, so one-way or two-way coupling. This is an example of two-way coupling. So you could have some frequency coupling with thermal. This is frequency response. So here you can see that one single frequency is used as different thermal time step, but you can also have a different coupling like this way. So you've got the thermal analysis and then a transient. And here is, for example, one electrical cycle, which is run here. And then we made some loss average that we use onto the next thermal step. This is what is shown here. So JMAG starts first by calculating initial temperature, send that to the magnetic calculation, run, I don't know, 20 or 100 steps for getting steady state in the transient, average the losses once the steady state is reached, give the losses to calculate the next time step of the thermal calculation and calculating the next temperature, and then the electromagnetic calculation is redone, and etc., etc. We can also make some coupling using some small multiphysics that could be done in Designer or in Express, and especially in Express Online. So small multiphysics, I will show you that, exactly what it is. And of course, you can do some mapping. So here is an example of mitothermal coupling. So I will show you this IPM example. So I will show you first the one-way coupling. So it means now, in this example, it's kind of weak coupling or one-way coupling. It means the calculation will be run sequentially. So if I show you here, you can see that you've got first the electromagnetic calculation. So if I go to properties, you see it's 3D magnetic flux density. I don't know if the zooming is working. Yes, zooming is working. So you can see it's 3D calculation, magnetic calculation. And if you check here in coupling, you see that two-way coupled analysis is not checked. And then you've got the thermal calculation. So in thermal calculation, you could have steady state analysis. So it means it's one step, no need to specify any initial temperature. It's directly going to the final temperature. And of course, we also have the transient thermal calculation. So it means now you need to specify initial temperature, you need to specify some time step division and etc. And what you could also see that it's using the same interface than the electromagnetic calculation. You see time step. So it's everything under the same environment, same user graphical interface. So that's very efficient to be used. And so now maybe we can switch to the next example, which is the two-way coupling. So in the meantime, I could show you the good point of the two-way coupling. So that's what we call in JMAG the analysis group. So is it open or not yet? That's not a good one. Yeah. So now you can see that you've got your solid model as previously, okay? And you've got your magnetic calculation and your thermal calculation. But then at the top here, you can create one analysis group. And this analysis group, if you go to properties, you will have the coupling options. So it means you can specify the average losses is made on the thermal. You can specify a range if needed, if you need to reach some steady state and if there are some transient state in before, so maybe the average has to be down at some step. You can also use different mesh. So it means you can control your coupling option. Also start time and end time could be different. So I think I have a slide on that. Yeah, here you see that you could have in this coupling same time step, same time interval, or you could have different time interval, different start and end time. So you can completely manage your coupling, your two-way coupled analysis using that. Of course, if I go back to the one-way coupling, here, this is the one-way coupling. So let's go back to this one. You can also create some analysis group here. As I show you, okay, maybe I need to duplicate the study because I have some results. So I will call it test. That's the duplicated electromagnetic calculation and maybe the transient as well. I will duplicate it. We call it test and just one case is enough. Okay. So I have created those two and I will include those as a group. So still I can create an analysis group. And here you see you can select if it is sequential coupling or two-way coupled. Of course, in our case now it's not two-way coupling, it's sequential. So you can here click, select those two, the one that tested I've created. And then in the properties of the group, you can specify the order. And of course, you need to run the loss calculation before, because in this sequential calculation, loss will be given as the heat sources to the transient calculation. Okay, and then of course, you can get temperature. So at the end of your thermal calculation, and as I told you, the heat sources will be the magnet, the iron losses into your rotor core, stator core, eddy current in the magnet, in the coil, and etc. So before switching to small multiphysics, I also would like to show you one more example. One example of airflow cooling. So here, because JMAG is not a CFD software, we cannot include in the simulation the air in the air gap, for example. However, we could use some heat transfer coefficient, and we could create kind of equivalent thermal circuits. So if you go now in the thermal calculation, so here you can see some classical condition like heat transfer boundary and etc. But you can also build a kind of circuit. And it means that now it's not an electrical circuit. You've got some kind of heat, let's say 1D equivalent thermal circuit. And it means that the part which is not represented, maybe I don't remember exactly, but here I think it's the thermal resistance, maybe due to the insulation layer or something like that. So it means you don't need to draw everything in your thermal model. And some phenomena that could not be represented in JMAG because no convection is handled could be handled by some thermal equivalent circuit. And here you can see that there are 3 different equivalent circuits, because in fact I have splitted this model into 3 different parts, and each stator core, for example, each transfer boundary condition will refer to different slices. And then I could also link all those circuits together and imagine that I can now take into account some air cooling direction. So this is the purpose of this thermal equivalent circuit. So to take into account parts that are not included in the thermal calculation. And so from this point of view, why not making the thermal calculation, all the thermal calculation as equivalent thermal circuit, equivalent circuit analysis, and to embed that into the electromagnetic calculation. So that we call the small multiphysics. And you don't need the 3D FES thermal solver in JMAG. This could be directly done into the electromagnetic calculation. And of course, you've got some coupling control. So it means that you could, in fact, you could ask JMAG to make the temperature calculation depending on different steps. But for the torque calculation and the electromagnetic calculation, you see that there are many steps in between the first step for the thermal. And you can also see that when the temperature is increasing, you can see that the torque is decreasing. Of course, you need to input some magnetic flux density dependency, thermal dependency for the magnet, and also for the resistance of the FM coil. So if you input that, then you can see that some temperature dependency will be implemented directly in JMAG. So I think I have one example here. I can open it. Okay, so now you can see that I have just one model, one study, and this is actually a 2D magnetic simulation. So no thermal calculation. And here, of course, you can add, you need to add some condition like heat generation density, heat generation component. So it means that now some thermal condition could be included in the magnetic calculation. And the circuit, here you can also see the different colors in the circuit. So the orange one means now it's kind of thermal calculation. And here you see that the resistance, for example, of the coil has some temperature dependency. And you can really quickly, with a very simplest way, evaluate the impact of the thermal into your motor using this equivalent thermal directly inside the magnetic calculation. And of course, you can see here the coupled. So it means that each 16 step of the magnetic calculation, one thermal calculation is made, and making some average loss on that, on the magnetic results. So for this, you don't need any thermal solver. It's embedded into the magnetic calculation. If you have a magnetic calculation, you can use it very easily and very quickly. Let's have a look on Express Online. So maybe you should know that Express is a pre-designed tool of JMAG. It's a mix of FEM, rough FEM calculation, analytical calculation. And this year, the equivalent, thermal equivalent circuit is also embedded directly in Express. So if I start new, so Online Express is, of course, it's online. So you can go to JMAG Express Online. So this website is available for anybody. You just need to create an account. Then you log in and you get that kind of interface. So as you may know, this is template based. So here you've got the different templates, different combination, okay, auto, rotor, and etc. So let's go for the basic one, IPM motor. And of course, now you can see this thermal is available. Thermal evaluation is available. So when you click on thermal, you've got that kind of equivalent circuit. And so if you solve the calculation, so the calculation is solved on the JMAG server. Of course, nothing is solved on your computer because that's a web page. And after the evaluation, you can get so your motor results, of course, as classical. So with some LD, LQ inductance, self-inductance, torque, efficiency, couple loss, magnetomotive waveform, and etc. And if you go to the thermal model, still if you go to characteristic, maybe you should know that the yellow boxes, that's for parametric calculation. So you can also run parametric. And now if you go to thermal model, you can see that you can evaluate the losses. You can evaluate the temperature in your model with this 1D equivalent thermal circuit. So please feel free to use this one. That's also a very, very good tool. Okay, maybe we will switch now to the thermal stress. So JMAG also can evaluate the thermal expansion. That's in the properties of the material. So you can get expansion due to the temperature. Of course, this is also a coupling analysis between electromagnetic stress and heat calculation. So you've got an example here that are available. Maybe I will skip it now and I will switch to induction heating. So maybe in aerospace, you need some induction hardening. So in JMAG, using some multi-frequency heating, you can evaluate the effect of different frequencies. So maybe low frequency will maybe hit your model very deep, and maybe highest frequency will be more intense, but at just close to the face, and you can include those both for the evaluation of the temperature. Many examples are available on the JMAG calculation website, but I would like to focus on this one, which is induction heating of this gearbox. So here is the gear. Okay, this is a partial model, and this is the heating coil. And you can see that you can make an optimization, not only just induction heating, but also optimization. So let me open this model. And thanks to this here grouping, so this is a two-way coupling, okay? And thanks of this grouping, you will be able, this group will be able to summarize all your response graph or CAD input parameter. There will be sent here into this analysis group. So here you can see that you've got the case control, which is available. And so you can go to parametric or to optimization. So let me close this one. That's the good one. So here is the model. Okay. So of course, I will have to restore the CAD link with the shape editor of JMAG. And now you can see that maybe I will collapse everything. And so you see you've got your analysis group here, which include your magnetic and thermal calculation. So those two calculations are there. And here you can see that some CAD parameter has been implemented. So those CAD parameter are coming from the shape. So if you go to the coil, so that's the position of the coil that will be changed. So if you edit sketch, so you can see that those parameters will be sent back to designer. And of course, in the thermal, some results will be also here calculated. That's a response graph, response data. So some temperature will be evaluating at different position. So that's coming from those probes, temperature 1, 2, 3. And so everything is sent back here in the response graph. Everything is sent back here. And if you go to case control optimization, you will be able to find all your input variable, okay, with those. So here are the frequency, the reference temperature, amplitude of the current, and you can specify some range and also position of the coil here. You can build some objective function based on those response data. So here you can see that some bias temperature is calculating, making some operation with the temperature from the different point 1, 2, 3, and also some diff temperature is also calculated. And we will try to minimize all those bias temperature and input current to get more uniform heating. And of course, we can select number of generation, population, multi-objective generative algorithm is selected. And of course, you can also distribute those calculations. And then when you review the different cases that have been calculated by the optimization of JMAG, then you can see different shape of the coil, which is implemented. And of course, you can also go to the results of each cases. And of course, you can generate, if you select two objective function, for example, Pareto curves. Yeah, for example, I did not run all the calculations, so maybe my Pareto is a bit small. Maybe I could make it as curves. So here in red, you can see the Pareto curves, for example, and you can see all the cases, and maybe you can check this one. You're interested in this one, maybe, so you can zoom, you can show the selected cases. So cases is automatically selected now, and you can make some investigation, maybe temperature distribution could be shown here. So you can see the temperature at different steps So you can see how the temperature is implemented, how the eddy current is penetrating. So for example, here you can make a new contour plot of current density. Okay. So you can see also how it is penetrating here, evolution of the eddy current. So thanks to this analysis group, you can run a coupled analysis, but you can also run kind of multi-physics optimization thanks to this analysis group, to this grouping. Of course, you can also check the correlation graph as well. Okay, so we talk about the induction heating, and last point is maybe the mapping. Of course, if you would like to run calculation into other software, you can map JMAG results onto third-party mesh. So we've got dedicated tool for Abacus, but any mesh could be implemented using some standard format. So we've got the multi-purpose file export tool for that. So let's go now to the short circuit analysis using RT. So we will try to get an idea what is RT, how to use RT. So we could use it with RT Viewer. We could use it in Simulink, so using some S function block, and maybe review the latest improvement of RT and a short example using RT as well. A short circuit example using RT. So what is RT? So RT is in fact building a behavior model, a high fidelity motor model for software in the loop and hardware in the loop. And this is generated and calculated from the JMAG FEA calculation. So in fact, if you've got a 2D or 3D model, it could be changed into a table or 1D model that could be included into your Simulink calculation. So here is the idea. You've got your circuit control given the voltage, and then using this RT table. So we will see that we've got different model of table. We've got the LDLQ model and the spatial harmonic. Then the table will send back the current and the torque. So the difference between the linear Simulink model, so it means you will have a sinusoidal waveform, constant rotor position, but using the JMAG RT, you will be able to have all the spatial harmonic due to the tooth, due to the magnet shape. You will be able to take into saturation, so you will have torque ripple, harmonics, and etc. So here you can compare. This is in purple, you've got the textbook or the linear model, and in blue you've got the JMAG RT calculation. That's the flux linkage, that's the induced voltage. So here in the induced voltage, you can really see the slot ripple, and same for the torque. So there are several devices supported by JMAG RT, and latest improvement, we added the wound field synchronous motor and generic model. So it means, however, whatever is the number of coils, you could create a RT model, or maybe for an inductor, for example, you can generate your RT model. It's supported any generic model, in fact. So regarding the three-phase motor, we've got the LDLQ model. So basically, it's based on the VQ and VD voltage and ID and IQ current to derive the LD and LQ model. So the limitation of this model is that no spatial harmonic is taken into account. And of course, we also have some error at magnetic saturation, high magnetic saturation. And we also have the spatial harmonic model. So now the torque results, it's not using some torque formula, it's directly the torque given by the result of JMAG FEA calculation. High order harmonic is taken into account for the torque, the inductance, and it's highly accurate, even if we've got some high saturated point. Here is the equation that are in behind. And of course, the inductances are differential inductances. So JMAG change a little bit each current separately to check the effect on the inductance. So you can compare, for example, the spatial harmonic model and LDLQ on the LDLQ axis. So you can see that this is the mid range and this is a high range. So you can see that, for example, the LQ inductance is not so well evaluated using the LDLQ model. And mid-range, you have some small error, but not so still reasonable. But high load, you can see that spatial harmonic is more accurate. So just to summarize each model, okay. So you can see that for the torque and magnetic flux calculation, the spatial harmonic has some current dependency, phase dependency, and mechanical dependency. So that's the most accurate model. Of course, calculation time is also longer than the LDLQ model. Here you can see that spatial harmonic is included for the inductance for the spatial harmonic model, for magnetic saturation, for the torque, and magnetic saturation for the torque. So all spatial harmonic are included in the spatial harmonic model. So of course, when the table is generated, it's encrypted format, so you cannot read it just opening the RTT file. So we've got what we call JMAG RT Viewer. So JMAG RT Viewer is free to use. You can download it on the JMAG website, and you can output that kind of map. So LD, LQ map, torque map, and etc. But of course, the main goal here is to use it in Simulink. So under the installation folder of JMAG Designer, you can get that kind of S function block. So we've got some electrical voltage, electrical signal input, voltage signal input, or current signal input. Please just keep in mind that even if it's voltage input, for example, this is current based. So the calculation has been made using some current. So here is just some voltage equation that are solved in advance, but it's still current based definition. Here is an example. So I will open you this example. Here is an example using this six phase motor. And here you can see that some fault will be implemented by this switch. So I can open you the model quickly. Okay, this one, and so here is the JMAG model. So nothing very special in this model. So you just could see the 6-phase definition. Okay, so here is the model, and then you see that I have just one study, and I have no results in this study. There is absolutely no results. Just a circuit is implemented here with the 6 different phases, 2 3-phase system, and JMAG RT will change. JMAG RT will change the voltage and the current inside. We'll change the circuit to drive the current with some circuit with some range specified in the JMAG RT. And I have also opened the Simulink model. So here is the Simulink model, and here you can see the fault here. So you can see here is the S function block. Okay, this is the model. So here you can see that the RTT file is specified. So it's a variable named RT. And this RT file is in fact saved in Simulink in this M file. So in this M file, I have loaded this M file, and this variable RT give the name of the RTT file. And this is the RTT file is the behavior table calculated by JMAG, And this RTT file is, of course, included in this working folder of Simulink here. And then you can see the two three-phase system, the number 2 and number 1 here. And here you will see that one fault will be caused at 0.2 model. And I will run this calculation. You will see that the calculation time is very quick. So you see that now I'm running calculation. And because of the RTT file is already made by JMAG, calculation is quite fast. There is not anymore FEM calculation which is called in behind, because they have already been done, and all the information are stored in the table data. So it means now Simulink is just calling some values in the table. So you can see that simulation could be very fast. And here you can also see the torque waveform. And here you can see that at 0.02, you can see the default is implemented. You can see the difference in the torque and in the current as well. And then if you check in the working folder, you will be able to get back the Gplot that have been it's using RT now. But then, yeah, you can evaluate the torque and the current due to this short circuit. The good thing is that now in JMAG RT, you can output any predefined quantities from your table. So for example, here you can output some vibration of the teeth, force of the teeth, to evaluate some pressure. But you can also imagine you can output some losses. Of course, the losses, some predefined, maybe you can see it here. I will try to zoom. So here you've got the user specified parameter here. So this is a generic model. But if you use the classical model, maybe I would try to zoom. It's not so nice, but you can see eddy current losses, hysteresis losses could be also outputted. And then you can also investigate your thermal design, having your control and having so your fault or something like that. So let's review quickly the new feature of RT. So this is a new method for shorten the calculation time. So we call that flux integration instead of spatial harmonic. Now flux integration is available, and you can see that calculation time is much more quicker for the table, generating the table. We've got, as I told you, the wound field motor and the generic model that can support any arbitrary model. The user defined output, the one I showed you previously, and you can also include some loss table. So of course, RT is kind of table. The table is made of several different operating points. So it's a kind of quasi-static calculation. The table is made from quasi-static calculation. So no transient effects are included in the RT table itself. But we have seen that we've got some very powerful loss table that could be calculated in JMAG with some preset 2 or preset 1 as well, but preset 2. And so it means that running some additional FEA calculation for including AC losses in the winding or preset 2 calculation, you can create some table that could be embedded into this JMAG RT. So it means that the weakness of this table is that it's quasi-static, so no transient effect are included. But thanks to this new feature, you can also embed it some additional table to get now accurate losses. So not only magnetic behavior could be accurate, but losses as well now with this latest improvement. So you can make a combination of JMAG RT and some loss table. It's completely embedded into JMAG now. So thank you very much. Maybe we don't have so much time for question. but feel free to ask. Maybe my colleague Didier and Corentin have collected some question or are ready to ask two questions. Thank you for your attention.
Thank you, Yves. Thank you very much for your presentation. So yes, I think we can anyway take some times to answer some questions. So we have a couple of questions regarding your presentation, Yves. So maybe you can answer to them, and Didier can also support. So the first question is, could you explain how the 2D and 3D model for loss calculation relate? Can we say that JMAG always overestimate the loss in a 2D model in comparison to a 3D model?
Okay.
So maybe Didier or Yves can answer to this question.
Yes. Sorry. Yes, I think in both cases, so JMAG can overestimate the losses. So it can overestimate the loss when you are using the standard calculation method. So when you are using the preset one or the FFT or apply loop, so it will overestimate the losses because it will make some extrapolation to get the equivalent loss or the ECC loss.
Okay, thank you, Didier. We can go to another question. Still about loss, I think. How is the impact of manufacturing of the iron core considered? Which method do you recommend for bulk iron? And the person said, I used the hysteresis model and got negative instantaneous values in some time steps.
Yes, for this. Sorry, for this for this question. Yes, into JMAG you have some option and some condition to take into account the effect of the manufacturer process during the error loss calculation. So there is some option to apply some correction in order to yes, to correct the error losses. Yeah. And for the negative uncertain value, I think maybe it's due to the mesh. So you need to check the
I think the negative value, I think that's due to the symmetric loop. So it's so the Hysteron play model is a purely mathematical model. So it means it has no. Sometimes it could have no real meaning. So if you, I think this is coming from your input, symmetric loop input. Even if the data included in JMAG has maybe some issue when, for example, the symmetric loop cross each other, it could become a negative loop. So that's an issue of measurement. But if you keep the average losses, which is positive, that's correct. You are still evaluating correctly the losses correctly. So some negative value, just one point, it could happen because that comes from the maybe not so accurate measurement. But it's very hard to get that measurement. But I think you need to focus on the average losses, and if you've got just 1 point, that's not a big issue. It could happen sometime.
Thank you. So the next question is actually, I think there is two questions on one, but how does JMAG calculate the excess loss factor? And is the material database only knows symmetric BH curve instead of loss curves?
Oh, could you please reply, Didier? I have some issue with my.
Yes. So the extra loss calculation is calculated from the loss property that you have into the material.
So in the material database, you don't have only the symmetric BH curve, you also have the loss curves, right?
Oh, and okay. Can you repeat the question?
Yeah, the question. So the first question is, how does JMAG calculate the excess loss factor? And the second one is the material database only knows the symmetric BH curve instead of loss curves?
Yes, that's so. When you use preset 2, it's using only the symmetrical loop. That's for sure. And regarding the tool, so when you need to calculate those coefficients yourself. At the moment, if I well remember, when you go to loss, is there this loss? It's here. Let me remember. So you need to calculate this coefficient yourself and then implement some table to implement this table into the JMAG material database. In the coming version, some tool will be implemented to compare the losses amount of the loss density and the symmetric loop, and then some coefficient will be calculated automatically. But at the moment, you need to specify this table.
Okay, thank you. Here, next question is, so if you have showed that a method to calculate the eddy current loss in lamination, the question is if we use SMC, so soft magnetic composite materials instead of laminated material, is preset 2 method still available?
So yes, for me is yes. You can use preset 2 for soft magnetic composite because in soft magnetic composite you have a different structure. So yes, so you can apply preset 2 for that for this kind of material if you know well the material property of each part of the composite part of the composite material.
Okay, thank you, Didier. Next question. The BH plots of the material accounting for the thermal effects are also modeled by JMAG, or these are required to be included by the user?
So into the JMAG material database, you have some example of material with BH curve depending on the temperature, but you can also create your own. So you can also create your own data. So you can create your own BH curve depending on the temperature and use it into JMAG for thermal calculation.
Okay, thank you, Didier.
So here is I show
yep.
the linear. So yes. You can have linear thermal dependency, or you can have BH curve thermal dependency. So I don't know, maybe I have some issue with the resolution. It's not so nice, I think. No. But
so
okay.
for the question about the impact, so maybe if you can show this option, residual strength magnetic correction. Residual strength. So this is an example of option that we use to take into account the manufacturer process into the during the iron loss calculation.
Yeah, that's maybe related to a previous question. And so depending on the distance to the cutting edge, you can have some correction factor. So this is calculated on the distance to the edge. And an adequate mesh could also be generated automatically. So you've got a kind of nice mesh, kind of layered mesh all along your edges, like this. Here I show with the mouse. So here it's not implemented here, of course, but you can imagine this is a kind of layered mesh which is implemented, and you will see that the B is impacted on those layers due to the correction, and also the losses could be corrected in those areas close to the shape. I think we've got some. We could send to the user if you have the email address, Corentin. We've got some white paper on that.
Yeah, of course. Okay.
Yeah, you can also find some example from the JMAG application catalog. So you have some example with the cutting process. So you will see how we correct we apply some correction to calculate the iron losses.
Okay, thank you. Maybe if you want to show something on the.
Well, you can continue trying to find examples.
We have a question about the thermal equivalent circuit. The question is the thermal equivalent circuit automatically generated, and can we modify it?
So it's automatically generated into JMAG Express Online. So
and is it possible to modify it in JMAG Express Online?
So I think you can modify the property, not the circuit.
Okay, and what about in JMAG Designer?
So in JMAG Designer, there's no automatic thermal network. So you need to create your thermal network into Designer. So
okay.
you only have it. You only have the automatic thermal circuit into JMAG Express Online.
Okay, so JMAG Express Online, just as a reminder, is the free version that you can find on the JMAG website.
Yes.
Another question, is there any way we can plot magnetic field variation in each axis, X, Y, and Z?
So can you repeat, please?
Is there any way we can plot magnetic field variation in each axis, X, Y, and Z axis?
Yes, of course, you can put some probes.
Yes.
And anywhere in your model, and you could have some okay, yeah, for example, here I can go to the MITIC calculation, and I could maybe make a new probe. So a new probe here, I place it here anywhere, so you can put some more points if you want, and you can go for MITIC flux density, and of course you can go for all component RMS X, Y, or Z, or you can go for cylindrical, and then you can also plot it versus cylindrical, radial direction, and etc. But if you go for all component here, you can then show it. I think I will have just 1 point because it's a frequency response, so I have just 1 point. Here you see that, in fact, this is just 1 point. It's a coupling with thermal. So I have several, in fact, the steps are now, in fact, time step, but it's for one single frequency. And then you can see the flux magnetic component for a different point and different axis direction and etc. RMS value, etc. Z, Y. So everything could be plotted.
Okay, thank you. Another question about the FFT method for loss calculation. Does only the fundamental of magnetic induction is used to calculate the iron losses?
Okay, could you please say it again? The beginning?
Yes. For the FFT method, does only the fundamental of magnetic induction is used to calculate the iron loss, the iron losses?
No, all the harmonic are included, not only fundamental. But it means, yeah, fundamental is detected, but then all harmonic are also used and included. This is maybe if I well understand the question, this is here. So you see that not only fundamental, but all harmonic are given. So if you use the FFT method, then you will have losses corresponding to all harmonic. If you use the apply loop, of course, apply loop gives directly the total amount of hysteresis losses. So it means that you don't have any harmonic when you use the apply loop. But if you check the eddy current losses, because it's still FFT, yeah, you will be able to get, of course, the total eddy current loss amount, which in fact are the summation. Okay, this is also an assumption. Summation of all harmonic. So I hope I well understood the question.
Okay, thank you. So let us know if you have any user question about this topic. The next question is about the JMAG RT. Could you give us an order of needed time to create an RT table or to generate an RT model?
Okay, yeah, of course, it's really depending on your mesh, if it is 2D or 3D, because it could be calculated in 2D, but in 3D also. So it's depending on the resolution, depending on the range you would like to calculate your RT, depending on the nonlinearity of your inductance. So if your inductance is variation or fluctuation of the inductance is really nonlinear, then you need more point to capture the phenomena. But with, let's say, a standard mesh and a reasonable range, classical motor, it's something like less than an hour. And of course, if you have many working point 3D model, of course, it could be several days or weeks, something like that. So it's really depending, but classically, it's something like 1 hour or 1 hour or 2 hours, something like that. If you've got very standard motor, standard mesh like that. So, and as I show you the latest improvement with the flux integral method divided by 2 the calculation time. So it's now a bit reasonable. Of course, if you have a very high mesh, high range and 3D motor, it could be weeks.
Okay, thank you, Yves. Another question about JMAG RT. How can JMAG RT losses can account the correct influence of current or voltage harmonics?
So as I explained, it's a quasi-static calculation. So losses, it's in fact just the losses classically embedded in JMAG RT. We are just scaling the non-load losses calculated at the non-load with the rotation speed, or not especially the non-load, but basically the losses are scaled versus rotation speed. So it means it's not very well accurate if you consider losses, because it's quasi-static calculation. RT is very good for evaluating magnetic point of view. This is why this those tables, so here, have been implemented, and so it means that at the same working point, if you are using exactly the same working point that's specified in the table, then you have the exact amount of loss that could be calculated in a full transient calculation. So I think that depending on the loss method used in RT, if you are just using the classical one or if you are using the additional tables, but of course, if you are using the more accurate loss table, if you match the exact working point, you will get the correct losses.
Thank you, Yves.
But anyway, yeah, it's hard to reply because I don't know if I will understand. But I hope it's replying.
Okay, so please contact us if you need more information. Of course, we'll be available after the meeting.
We'll be pleased to continue the discussion by email or another face-to-face meeting if needed, because it's hard to fully understand the question just by chatting.
Okay, next question. So we go back to the loss calculation. Someone said, I was doing iron loss calculation with a custom material and I got negligible hysteresis loss using the apply loop method.
So customs material, then yeah, it's okay. When you create your own material, it's maybe depending how you, so if you create a new one, then you need to specify losses, and you've got several methods. Iron loss calculation, so you can specify those Stemnitz coefficients of the coefficient of the Stemnitz equation, or you can specify some table. Maybe you need to check first the unit, because it's watt per cubic meter, not per kilo. So sometimes that's an issue with in the model coming from users. So you had better to check first the unit. Yeah, that's my first comment. Please check the unit. Check the unit also of the coefficient. Please note that well, JMAG is still using watt per cubic meter, so that's sometimes the error made by the user when you create your own material. And then, of course, we need to check the model in more details if the units are not the issue. Yeah, feel free to send us the model. But my first comment would be to check first the unit.
There is actually one comment about this question. So it's from the same user. He says, but the apply loop methods doesn't use loss data, as I understood.
Yeah, so then yeah, we need to check the model. So maybe we need, first thing then to check is to maybe put a probe here in one element, so you can focus on one element of one tooth, and you can check the flux. You can check how the flux is changing. If there is any, you can put some BH probe like that. So here in JMAG, you can go to probe. You've got directly BH probe. Now it's no need to create a B probe and a H probe and then to combine it. You can directly go to new BH probe and to check how the behavior of the B and H. And then check maybe also the settings of the electrical basic frequency to evaluate the losses. If you go to, do I have something open here about preset 1? So if you go to preset 1, you still have some basic frequency here to be specified, or you can specify angular velocity and number of pole. So you can check that you are using one electrical cycle. Here you've got some option here to specify start and end step. Maybe you've got some transient state, I don't know, in your transient calculation. So if you've got some transient state, maybe the flux is not completely established or something like that. You can check also the time periodicity. I don't know if you have specified any option like that. And if you used also different coordinate system, that could be an issue. So, so sorry, I cannot reply directly. Many things to check, but yeah, that's my advice. Check some settings here. Check the behavior of the B at some point, and then check the setting of the iron loss to check if you have correctly set up your loss calculation based on the behavior of the B you have displayed before. So covered one electrical cycle, no transient effect, and etc.
Okay, I think if need, we can set up a separate meeting to solve this. So please feel free to contact the technical support, and they will answer to you directly. Just I would like to come back on one of the first question. It was about excess loss, and I think we misunderstood the question. So I will rephrase it. How does JMAG calculate the excess loss factor if the material database only knows the symmetric BH curves instead of loss curves?
That's I think I show later on. This is something to be specified in JMAG directly, the coefficient. So here you can see that I'm in preset, which one? This one, yeah. So here, for example, I have this material which has been created here. And you see that here, when you now go for the symmetric loop here, okay, there is some additional table here, anomalous eddy current loss table, coefficient table. That's the correction coefficient. So the user has to specify it manually at the moment.
Okay, thank you. Another license. Yeah.
Still versus frequency and magnetic flux density.
Thank you, Yves. Another question is about license for JMAG-RT. So which license do I need to create JMAG-RT table? So this I can answer directly. So there is a specific license module called JMAG-RT that you need to generate RT table. And the second part of the question was, may I use multiple processor cores? So yes, of course, multiple processor cores is possible and can be very useful to decrease the duration of the RT table generation. So
you can also distribute all cases, all working points onto several different CPUs, but you can also use several CPUs to calculate one working point. So imagine you've got 50 calculation, you've got 100 CPUs. You can use 2 CPUs per calculation, and then finally you can run 50 calculation at a time. So you will use 100% of your 100 CPUs. So you can You can distribute cases, but you can also use several CPUs for each cases. Could be a combination.
And to answer to the new question about this, so if you distribute several cases, you need several license, several solver license, for example, TR for 3D or DP for 2D. But if you distribute one case on several cores, you need, in this case, to use a parallelization license like SMP PA2 or MPP.
And maybe you can talk about the power simulation license.
Yeah,
so
good idea.
PSL, power simulation license, is very dedicated to that kind of parametric calculation, because in fact RT is kind of parametric, several working points, so it's kind of parametric. And of course, if you would like to run 100 cases at a time, you need 100 solver, and it will cost you a lot. So this PSL decrease very significantly the price for I think it's 100 license package.
Yeah.
And it's the price
so
of corresponding, the price is corresponding to something like 10 or 12 solvers. But that's not, the 100 solver are not independent. So it's really for parametric calculation or RT. That's why the price is reduced, because it's not independent. But it's very cheap compared to buying 100 solver.
Yeah, indeed. Thank you. Next question. When hysteresis cycle is used in the analysis, is it only static hysteresis? And how does it affect time computation, or computation time?
Yeah, so that's indeed the static hysteresis. And calculation time, yeah, it's, of course, you've got some more iteration. So the shape function identification are made at the beginning of the calculation. So it costs a bit of time and maybe some more iteration. But it's not so big. Not so big time increase.
Okay, thank you, Yves. So it looks like we've covered all your questions. Okay, actually, maybe we just received a last question, so maybe we can answer to it before to stop. So to reduce the calculation time, can we solve the loss analysis with quasi-static analysis rather than transient?
Yes, of course, it will reduce the calculation time, but so yeah, what do you mean by quasi-static? Do you mean preset one or?
Okay.
But yes, I think of course it will shorten the calculation time if you run some quasi-static calculation. Don't fully understand the meaning of the question. Sorry.
Okay, that's fine. So if you want more information, again, please send us an email, and we will be happy to answer to this. So I think we can close this session. Thank you very much for your attention and all the questions. I think it was very interesting to answer to all of them. I would like also to remind you that at the end of the webinar, you have the possibility to give your feedback on the presentation and specify if you wish to have a technical discussion with our technical expert. So this is a way to keep discussing. I would like, of course, to thank our speakers today, so Sergi and Yves. Thank you very much, guys. And thank you to all the attendants. So we really appreciate to have you during this webinar. Thanks again for joining us today, and we will see you next time. I hope you all keep safe during this unusual situation and period. and we will be happy to see you again when everything will be back to normal. Thank you very much, and see you guys. Bye-bye.
Bye. Thanks for your attention. Bye.